Welcome back. In this chapter we will talk about the high fuse that we somehow avoided for most of the times. Probably from all the fuses, this one has the highest potential of making the ATmega unusable, so we have to be extra careful. What will we get in return? In return, we will get the option to debug the user program, and in this chapter we will see how to do that. This is the outline. First, we are going to talk about our current methods of debugging, what the advantages and disadvantages are. Then we will talk about simulators, and in the end we will head over to the most extensive options available in ATmega debugging, the hardware debuggers. How do we debug usually? Some of us might use plenty of printf calls in the code to follow the flow within the program, to, for instance, hunt down one of those infamous segmentation faults when trying to debug C programs for the PC. In Arduino, the printf equivalent is Serial.println, and to find a bug, sometimes the entire program is filled with print lines showing the execution path or variable values. Or what I personally often use is the onboard LED. Is the ISR executed is answered by an LED toggle. There is a problem though for all these methods shown here. They require computation resources which have a limit, or we are simply too slow to see the change. What if the ISR is executed so fast that the LED blinks but it is invisible to the human eye? Or I have multiple ISRs. Does every ISR get its own LED status? What if there are no pins left? Or if the transfer speed of the serial UART interface is too slow to return every tick in the timer? And we have to keep one more disadvantage in mind. Those insertions change the behavior of the program. For instance, if a program is implemented that bit banks a particular protocol, inserting an UART instruction confirming that a pin changed its state takes time, maybe longer than the bit banked protocol allows. Another option is utilizing the GDB to help in debugging the code. We already used this debugger in a lecture to show how the stack is overwritten. It allows to examine the content of the memory or variables, set breakpoints where the program is to be stopped after it started executing to allow a closer examination, or to step through the instructions of the program one by one. This debugger helps in checking the internals of a program without inserting extra code by the developer. It would be helpful if the same functionality is available for ATmegas. And it is, as we will see in a little bit. However, the problem is not debugging the user program. The problem is how to execute this program in the first place, as it cannot be executed on the PC. That is why there are simulators, which simulate the behavior of the ATmega. In this chapter, I would like to show two of them which are readily available in many Linux distributions, that is simavr and simulavr. I already installed them in the Ubuntu that is installed in the VirtualBox image. First, let me show you simavr, and in the second half of the session also a bit of simulavr. So let me go to course, simulators and blinking LED. And there are 4 directories. These are different implementations of the blinking LED, and the source code for simavr is included in this directory. We come to this in a bit. First, let us have a look at the blinking LED delay. So here I have my C program for the ATmega. I have a makefile, and I have a text file whose content we also discuss in a little bit. First, let me show you what's inside that C file. And as you can see, there's nothing special. I configure the data direction register of the pin that's connected to the onboard LED as an output, and then this pin will toggle every 10 microseconds. For later purposes, let me display the line numbers, and for that I use the command setNumber, and let me open a window in the same directory. Okay, let me move that to the side, maximize this. Okay, now I just compile it by invoking make, and let's see what happens. Okay, so I have my compiler here. I added the -g option. -g adds the symbols for debugging, and the symbols are now included in the binary file. I invoke avr size to see the program size, and then the makefile also starts simavr with the frequency, which is the same as this one, that is 16 megahertz. The MCU I'm going to use, that's the ATmega 328p. The -g parameter indicates that I would like to attach avr-gdb to it, where both output for the simavr and the binary file that is supposed to be simulated. Then the simulator loads the program, there's 152 bytes and 0 for data, for the global data, and here it says that the AGB in it is listening on port 1234. So we have to remember that port because we are going to connect avr-gdb to it. Nothing else is going to happen in this window, so I just minimize it and open again a new one. Now let me invoke avr-gdb and as parameter the blinking LED.elf. So we see here that this GDB is compiled to run on a PC, on a 64-bit machine, but the target is AVR. And it also loaded the symbols from the binary. What can I do here now? First, I can browse through my program by using the command list. So it shows the first 10 lines of the program. If I want to show some more, I can use list plus, and it shows the next 5 lines, but here only 4 because the program ends at line 14. That's the last one. Or if I just want to see what is around a function call, I can do list and then main, because main is the only function that I have at the moment, and then it will display a few lines around the start of main. Or if I want to display a particular line, I can use list and then the line number, let's say line number 6, and then it displays some lines around line number 6. Now I would like to debug the program, and for that I set some breakpoints where the program execution is interrupted. And just as an example, I would like to set a breakpoint before the instruction in line 6 is executed and before the instruction in line 9 is executed. And for that I use the command B for breakpoints and then the line number. So in this case it is 6. It creates breakpoint number 1 at a particular address, in this case 80, in the file blinking LED_delay.c. And then I do the same with line number 9, and I have 2 breakpoints now. Okay, to run into the breakpoints, I have to execute the program. However, this binary here is compiled for the AVR. Hence, I cannot execute it on this 64-bit machine, but I have to execute it on an AVR architecture, and for that, this simulator comes into the play, which waits now in the background for any connections from GDB. That means I have to create a connection from this window to the simulator which is running in the background. And to do so, I use the command target, and it's a remote, which allows me to specify the address. However, since it's running here locally on this machine, I can use localhost, but I can also just omit it and then tell GDB at what port number the simavr is waiting for us. And the port number is 1234. 1234. Okay, the connection has been established. Now the program counter is currently waiting at 0, and that is where the interrupt vector table starts. So if I just suspend it for the time being and show the disassembly using avr-dump of my binary, pipe it through less, we see that the program counter is waiting right here, which is this address, and the first instruction is basically a jump to address 68, which is then here. So the simulator will execute this part and then jump to the main. And this is the main, and somewhere is my DDR configuration, that is right here. That means at address 80 the breakpoint is set, and at 82 the other breakpoint is set, which then configures the toggling of port B5. To see the source code lines in the assembly, you can use avr object dump -d, and you add the parameter -S, and then the source code is also displayed. So for instance, the source code in this line created these instructions, and here we see, for instance, the delay, and then it jumps back to address 84, which is then here, which is doing again the toggling. Let us execute the program in the simulator, and for that I use C, that is the short form for continue. And you see it was executed, and we hit the first breakpoint. Now what I can do is I can display the values of, for instance, the register DDRB. I can examine them by using the command print and then DDRB. And currently it is 0. The output is in decimal, so if I want to have it in hexadecimal, I can use print/x, and then it will be displayed in hexadecimal. Or in binary, it's then T. So all of them are 0. If there are issues with any command, GDB has extensive help options. For instance, for more information regarding the print, you can use help and then print, and it will tell us what it does. Or if I want to know how many output formats are here, so I use this X, I use the T, but is there anything else? You can use help and X. Then we'll see there's an octal, hex, decimal, unsigned decimal, and so on and so forth. Okay, now the execution waits here, and in one point in time I want to proceed. And what I would like to do is I would like to step through the program step by step. There are basically two commands for that. One of them is next, and the other one is step. The difference is that step is stepping through the program until it reaches a different source line. That sounds already very nice. The short form of step is S, and it also accepts a parameter that is N, and N indicates how many times step should be executed. So if I say, for instance, 10, I don't have to hit S 10 times. I can just write S10, and then 10 steps will be executed. The other command was next. And next is, unlike step, it also steps through the program, but it does not enter subroutines. So for instance, this one is a subroutine, and I don't want to debug delay US. I would prefer to step over it, and hence next sounds a lot more appropriate than stepping. So let us try to step through the program. Currently we are at the breakpoint before this instruction. And for that I'm using next. And as you can see, we are hitting the second breakpoint now, which is before this instruction. That means we executed this one, and I should be able to print it and see the new value. Then next, it will be the delay, which will be jumped over, and I keep executing. And if I print port B, you will see that it toggles from 20 to 0 in hexadecimal format. To take a shortcut and to avoid writing print all the time, there's another command called display, same format parameter, and then port B. And whenever the GDB prompt, that is this one, is displayed, then automatically the port or the variable that you put into display is being watched and then displayed. I can add another one, for instance DDRB, which does not change at all. And whenever I step through the program, you see that both are being displayed. To exit GDB, we can use quit, and then yes, so we are attaching from the remote, and I can switch over to the simavr and press Ctrl+C to terminate it. I collected all these commands that I used and a few more in the useful gdb commands.txt, which can be displayed with less, and there I describe them a little bit for your reference. So avr-gdb in conjunction with simavr allows me to examine the behavior of the program easily. But what about periphery and interrupts, which are essential for embedded systems? Let's test it out and move to the other example that I have, and that is blinking LED underscore ISR. Again, I have the useful GDB commands. This time it's a link to that file that we saw earlier. And I have two makefiles here now, one for simavr, and we are going to try the same program for the AVR later also in the other simulator, the simulavr. Okay, let me change the directory here as well, and let me compile it. Now, since I have two different makefiles, make doesn't know what to do, and it expects actually a file that's just called makefile, and I have to specify the makefile that I would like to use, and I chose makefile simavr. It compiles again and starts simavr. But what is the content of this C file? Let me switch over to this directory. ISR, NVI, linking LED ISR.c. Again, show me the line numbers. This program has the same functionality as the one before, except that the blinking now is every second. I moved the blinking functionality into the ISR whenever there's a compare match, and I'm using the timer, which is a periphery. So I'm setting the register of the pair match unit, and I activate the local interrupts, configure CTC mode, and a prescaler of 256, activate the global interrupts, and here I added a NOP instruction. That is basically an instruction that does not have any side effects. And I did this because otherwise the while loop will be empty, but I would like to put a breakpoint here, and for that I need a source code line, and I added the NOP in assembly there. So this is a test, and here's a prescaler of 256. That means there are 256 clock cycles before the counter register is incremented. But for testing purposes, I don't want to step through this program so many times, and this is basically 256 into 31,000 clock cycles, or even 63,000 almost clock cycles that need to be simulated before the ISR is executed. That will take a bit of time, and that's why I'm reducing the prescaler to 1 for the time being. And what I also do is I reduce the compare register so that the comparison is faster. Obviously the LED will not blink in a second interval anymore, but what I want to test is if the simulator can execute this ISR, and I just shorten my wait time to do so. Okay, that means I did some changes. That means I have to recompile it. So I exit it with Ctrl+C again and just execute the same makefile. Did I save it? Now it's saved. And now let me execute the make again, and the simulator starts and waits at port 1234. Again, I have this -g parameter to include the symbols. On the other side, let me start in gdb with the binary. Again, I connect it to the remote, and now I'm going to set the breakpoints definitely in this line so that I know that the ISR is being executed, and I set a breakpoint right here before the SEI, and where this no operation is mentioned, that is line 28. Let's start the execution, and I hit the first breakpoint. Now the program counter sits before this instruction. So what I can do is, again, can check out if the registers have the right values. For instance, here the configuration register of timer 1, it's currently set to 9. This is the first bit, and this is the fourth bit. So in binary, it will be 1001, and there we go. So that is as expected. What I also want to display is actually the counting register. And now I start stepping through the program. So I'm hitting the breakpoint for NOP, and I see here that despite the prescaler is set to 1 now, so the TCNT should increment every clock cycle, it is still 0. I do it again and again, and it remains at 0. And even if I do it like 1,000 times, it's still 0. So it seems that the value in register TCNT1 is not simulated. But let's see if the ISR is executed, and for that I delete the breakpoint that I have here with delete breakpoints. So I just type a little bit of the command and then hit tab, and it completes it automatically. And this breakpoint that I set here was the third one, breakpoint number 3, and that's why I specify here the 3. Breakpoint deleted, and let us continue till we hit the next breakpoint. And here we see that we hit breakpoint 1, and that is port B. That means the ISR was indeed executed, despite that the register value of the timer is not simulated. So it seems that the behavior of the timer is simulated, but not its functionality. Or there could be a bug in the program. The problem with simulators is that they can simulate the behavior of the MCU. But what if the behavior is triggered by some changes in the physical world, or the MCU is supposed to change something, such as the state of the LED that we have in this example? We can print the registers, but how will we make sure that the LED will indeed glow without seeing it? Therefore, simavr can be extended to simulate also the environment. Let me show an example. So I exit here again and terminate simavr. And we have here the third directory called simavr. Let me show you what is inside here. Here I have my blinking LED program with the interrupts. Let me show you the content. Blinking ISR. This time I'm using the correct prescale of 256. So instead of CS10, here is CS12. And I use also the correct compare values. So let me compile it. Again, I have multiple makefiles, so I have to choose the makefile for AVR. So it compiles everything and starts the simulator, but this time I just terminate it because this time we use a different method. And that brings me to the other C program that we have here. And this one contains the simulations of the physical environment. Let's have a look at it. It might be a little bit overwhelming, but let me go through the major points. First, I'm defining what the binary of my AVR and blinking LED program is, and I define the frequency and the MCU. That is equivalent to the parameters that I used to invoke simavr earlier. Then I have some status messages, what's this one or this one, if something goes wrong here. The AVR simulator is initialized and the firmware, that is my blinking LED program, is uploaded into the simulator. Then I have a GDB session here, so I started at the same port, 1234, and initialize it. Then some printfs here, and then the simulator starts in a separated thread. What I also have here is a hook. So we skipped this one. This means here I'm registering an interrupt that, if it occurs, should notify me. What is the interrupt about? If there's a change in the output in port B and pin 5, then IRQ LED status is supposed to be called. And this is a function, and it does not take any additional parameters. That's why null is written here. What is in this function? It is mentioned on top. it is right here. So it computes the simulation time since start, and then just have a printout. And what does it print out? It prints out the current simulation time and the status of the LED at port B5, and it also prints out the current value of the pin of port B5. It could be any functionality here in that C function. For instance, I could attach an Arduino to the USB port, which then takes care of its onboard LED if the IRQ hook is called and the data is transmitted through USB from the PC to this Arduino. For now, I just print the kind of IRQ that happened and the current value of the pin. Let's compile this. And this time I have to use the makefile simavr. And instead of avr-gcc, I use the normal one so that it can be executed on this machine. Now I have two executables. This is the one for the AVR, making the LED blink, and that is my simulator. And if I check what kind of files it is, you can see here that this ELF is an ATmega AVR 8-bit executable, whereas this file is an executable for x86 64-bit. That is this processor architecture of this computer. Let me execute it and let's see what happens. Oh, simavr. So it prints out the messages that I showed earlier. This is the port, and here you can see how it changes the status. So this IRQ hook is called round about every second, and the LED status toggles. So the simulator issues the IRQ on time every second. Therefore, simavr is able to simulate the behavior and not necessarily all the status updates. And it is able to do so because of the sleep call that is included into the avr program. Let me show you. So there was one more modification compared to the program earlier, and that is I'm setting the sleep mode to idle, and then in this while loop I'm executing sleep mode. The simulator knows that if the ATmega sleeps, it does not have to simulate anything, but just has to wait till one of the interrupts wakes up the simulator. Therefore, it is much faster. In fact, simavr also knows that if sleep mode is called without activated global interrupts, so if this is for instance removed, that this program will never wake up from its sleep, and therefore simavr exits gracefully without the interruption by Control and C. Okay, that's all about simavr. What about simulavr that we had earlier in blinking ISR? And this was simavr. Let's invoke simulavr and let's see what happens. Okay, let me compile it. Make -f and then the makefile for simulavr. And now, as you can see, it waits at port 12 and 12. Let me put this again in the background. Let me reorder it. Okay. What's the content of the C program? So that I know where to put the breakpoints, and avr-gdb blinking LED.elf target remote. This time the port is 12 and 12. Okay, the PC is at address 0 and the program is ready to be executed. I would like to know if the ISR is executed again, so I put definitely a breakpoint before instruction in line 5, and I put another breakpoint in 28 again, and then I execute the program till I hit the breakpoint. What I would like to show is the difference between simulavr and simavr, and for that I use display of the TCNT1 register, and you see that this value is already 3. In simavr this was a constant 0. So if I step through the program once more, you see it becomes 6 and 9 and so on and so forth. Let us see if the ISR is executed. So again, I delete the breakpoint, and this was my second breakpoint, and I keep running the program till I hit the next breakpoint. That is then hopefully the one that we placed here in this line. And it looks like as if the ISR is executed. TCNT1 is equal to 20. So it went up to 2499 because I'm compiling with 16 megahertz. The TCNT1 was reset to 0 and the ISR was executed. And if we step one more time, TCNT1 becomes 24. At this point, the breakpoint was before the instruction. I stepped one further, so this instruction was executed, and now we are basically between line 5 and line 6. But the timer incremented from 20 to 24. Why is that so? Let us examine what instructions are actually in the ISR, and for that I use again avr object dump for this assembly and show me the source code in between, and the blinking ISR.elf, pipe it through less. So the ISR is located at address 80, so let me scroll down to address 80, here it is, here's my ISR, and here's my instruction. These 4 instructions shown here are representing the functionality of this source code line. What happens here? The value at address 5, that is the address of port B, is stored in register 24. The constant of 20 in hexadecimal is loaded in 25. Then the XOR is performed, and the new value of this XOR is written back from register 24 into the address 5, which is the port B. And due to the new value, the LED attached to port B5 toggles. As you can see, there are 4 instructions, and it seems that every instruction requires 1 clock cycle. In the meantime, while these instructions were executed, the timer incremented by 4, because the timer increments with every clock cycle. Quiz question: at the current location, how many instructions does it take to come back to the NOP that we inserted into the while loop? Right here. We see here is the no operation inserted by this source code line. How many instructions? What will be TCNT1? A little hint: not every instruction can be executed in 1 clock cycle. And to know how many clock cycles instructions require, please refer to the reference manual. There is a chapter about the instruction set summary. These are all the instructions that the ATmega supports, and the number of clock cycles is mentioned in the last column. And that concludes the practical session, which just gave a short overview about simulators and GDB. GDB is very powerful and it takes a little bit time to get used to it. Let us return to the lecture to summarize the session about the simulators. Simulators provide a relatively easy debugging mechanism for a program. Basically, there are two types of simulators, time and clock accurate ones. While simavr seems to be time accurate, simulavr looks like as if it is more cycle accurate. For instance, in simavr, the ISR was executed every second, but the timer did not count till the correct value to execute the ISR. In fact, it did not count at all. The simulator recognized that the developer wanted to execute the ISR every second and simulated that behavior in time. Simulavr follows a different concept. It simulates the timer and hence requires quite a bit of computation resources to execute the ISR. However, whatever policy the simulator follows, there is a major drawback, and that is the periphery. Embedded systems interact with the physical world closer and more often than PCs. In fact, the environment can easily influence the behavior of the program. There is a myriad of sensors and actors out there which can interact with the ATmega. How to simulate a program that reacts to stimuli? While it is possible to implement behavior of peripheries in C and easily integrate them in simavr, the software developer must decide if it is worth the time and effort. There is always the danger that the model of the periphery is too abstract or too ideal and hence its behavior too distant from the actual hardware device. Maybe the ATmega user program is debugged to run with the simulated periphery, but it will not work with the actual one. Therefore, it would be a good idea to have the option to peek and step through the actual user program that runs on a real ATmega. While PCs have plenty of resources left over when debugging a program with printfs or GDB, the processors in embedded systems often do not have the computational resources for expensive data transmissions of variables or to slowly step through the program. In addition, due to the interaction of the embedded system with the physical world, it is better to eliminate bugs while the system can interact with the world. Otherwise, the question might arise if a developer debugs the user program or the abstraction of the physical world. And here the JTAG comes into play. It is a widely used and standardized protocol that allows to connect a debugger to an embedded system. But not only to embedded systems, JTAG is established even among FPGAs and many other powerful development boards. Besides from supplying an independent clock through the TCK line, it also has wires to transfer data in and out of the unit under test and to select the test mode through TMS. Although there are JTAG variants available which require less wires, attaching a JTAG adapter to an embedded system becomes increasingly difficult the lesser pins the system has. For instance, the ATtiny has 6 pins available for data transfer. That pin count includes the reset pin, and some of the pins might be already used to communicate with periphery. Disconnecting the periphery to make room to attach a debugger is exactly what we wanted to prevent, since we would like to test the MCU in its habitat. Therefore, Atmel, the initial company releasing the ATmega, came up with a proprietary protocol called DebugWIRE and equipped all its MCUs that have a low pin count with it. It just needs one wire, bringing the pin requirements to a minimum. So where is it in this diagram? The DebugWIRE interface is connected to the first pin in the ATmega. and hence shares the pin with PC6 and the reset. First, the advantages. Using a pin that is usually not used by any periphery seems to be a very good idea. No replanning or redesigning of the periphery connections nor alterations in the software are required. Now the bad news. It is using the reset line. How do we reset the ATmega now, which we need to do every time we would like to reprogram the flash once we found a bug? And finding a bug is very likely as the program is currently being debugged. How can the functionality of the reset be diverted and the pin reused for debugging purposes? That brings us to the high fuse of the ATmega. Please note that for the ATmega 328P, the functionality is located in the high fuse. It might be different for your MCU. Please refer to the reference manual just to be sure. We have to be a bit careful if we would like to reprogram the ATmega, as we can lock ourselves out from reset and reprogramming it. We already discussed the boot asset bits, defining at what address the bootloader is located and what size it is. So far, we omitted the more significant part of the fuse bit. There is the reset disable, which disables the reset functionality of pin 6. If the reset functionality is disabled by programming this fuse bit, the pin becomes a normal I/O pin. Usually, a low signal on this pin will issue a system-wide reset, and if the pin carries a value of logical 1, the ATmega operates normally. The question is now, if the pin is a normal I/O pin, how is the ATmega reset? The answer lies in the electrical characteristics of PC6, which are slightly different compared to the other pins. It basically accepts 3 states instead of the binary 0 and 1. It accepts logical 0, logical 1, and a high voltage of 13 volt. If the fuse is programmed to reset the ATmega, a high voltage programmer is required, which is able to supply 13 volts to the reset pin. On the right is an example for the STK500, which has this capability. This one shown here is a custom-made copy of the original programmer from the manufacturer. The next fuse bit is DWEN, which enables the on-chip debug system called DebugWIRE. There are a few constraints to be considered when using the DebugWIRE. First, if that fuse is programmed, there is no reset anymore available through this pin. Further, the main clock selected by the clock select fuses remains enabled even during sleep. Hence, measurements involving the power consumption will not return with realistic results. In addition, the log bits, which we have only talked about a little bit regarding the protection of the flash and EEPROM against downloading or altering the memory pages, need to be unprogrammed. And there is something that we need to be very careful with. The DWEN fuse cannot be unprogrammed through the DebugWIRE interface. The DebugWIRE can be temporarily disabled though. However, with the fuse set, the debugger becomes active again with every power cycle. Therefore, to unprogram the fuse, the DebugWIRE needs to be disabled temporarily to reactivate the ISP interface. In conjunction with the next fuse bit called SPIEN, which, if unprogrammed, disables the option to program the ATmega through the ISP interface, that could create a dilemma. Imagine that this SPIEN fuse bit is unprogrammed, even just accidentally. That means that we lose the option to reprogram the ATmega or unprogram the debugWIRE fuse. So it is a very good idea to leave the SPIAN fuse bit programmed. If that value is modified, a high voltage programmer is definitely required to bring the ATmega back to life and to make it responding to an ISP programmer again. Okay, once the DWEN fuse bit is set, what are the next steps? We need to attach a debugger to the debugWIRE pin to do something useful. One debugger is the ATmega ICE, which is 100 to 120 euros or about $150 investment. It allows to connect the avr-gdb that we saw in the session about simulators to avr-gcc, which acts as a proxy between GDB and this hardware debugger. Alternatively, it makes the debugWIRE available in ATmega Studio, the development environment for Windows. This ATmega ICE is the successor of the quite popular JTAG ICE MK2, which is still available in various online stores, either as second-hand original or as a more economical copy. Alternatively, developers used the avr-Dragon board to access the debugWIRE interface. The avr-Dragon, also discontinued at the time of this lecture, but still available in online stores, is a programmer and debugger for AVR devices. Apart from debugWIRE, it also supports JTAG, ISP, high voltage serial programming, parallel programming, etc. However, not to compete with the more expensive ICE debuggers, the JTAG of the avr-Dragon does not support MCUs with a flash memory larger than 32 KB. Luckily, the ATmega 328P is still in that range. I'll copy the link that you see here on the slide into the resources folder. The link describes how to make the debugWIRE available through the Dragon board and gives a step-by-step instruction manual. However, all those hardware debuggers will set you back around 80 to 120 euros or 100 to 150 US dollars. While that is a good investment for a professional AVR software developer, it is a major cost for the occasional hacker. Aren't there any alternatives which are less expensive? Although the debugWIRE protocol is proprietary, it has been reverse engineered. Conveniently, Mr. Wayne Holder implemented a sketch called DebugWireDebuggerProgrammer, which, if loaded onto an Arduino, acts as a hardware debugger and programmer. While the Arduino ISP is a programmer, the DebugWireDebuggerProgrammer is a debugger with the capability to program through ISP as well, to unprogram the WEN fuse again, for instance. The best part of this solution, since it is open source, it does not cost us anything. I'm going to place a link to Wayne's tinkering page into the resources folder. The video that you find on his page is definitely worth a watch. However, there is a drawback. The hardware debuggers introduced in the previous session are all compatible with avr-gdb. Hence, instead of using a simulator, the real MCU can be utilized to step through the program while it is interacting with the periphery. Currently, the GDB functionality is not available for the DebugWireDebuggerProgrammer. But since it is open source, maybe someone will implement a GDB interface to it. That would be awesome. But let me show you how it works. If you would like to leave the ATmega whose user program is to be debugged in the Arduino development board, you can do so. However, to be successful, the decoupling capacitor needs to be disconnected from the reset line. To do so, you have to unsolder or cut a link on the Arduino board. Be careful with a knife and avoid cutting any other traces on the board. Since the cut to be made is so small in the demo, I'm therefore using the standalone ATmega from the previous exercises. I'm going to connect the ISP interface, as well as the debug wire and power supply. I copied the code for the DebugWireDebuggerProgrammer to the shown directory in the VirtualBox image, or it is also attached as usual to the resources folder. It is a bit different to the one that can be downloaded from GitHub. I added the functionality to read out the extended I/O as well, as we will see in the following example. I have here a setup. This is my DebugWireDebuggerProgrammer. This is my 328p, currently running on 8 MHz. I attached a green LED to port B0 that is in blinking. This red LED means that power is currently supplied to the board. I have here a 15 kilo ohm pull-up resistor. And what are my connections? The yellow ones here are my ISP connections. This is my debug wire connection. Power also comes from one of the data pins. And this is ground. Interestingly is this wire here. If this pin is floating, like it is currently the case, this DebugWireDebuggerProgrammer is an ISP programmer. And if this wire is connected to ground, then this becomes my debugger using debugWire. Currently everything is pretty normal, and I can use ISP to upload the blinking LED program once more. So let me show you how the DebugWireDebuggerProgrammer can be used. For that, we go to Course, Simulators, DebugWireDebuggerProgrammer. There are two directories. First, let us check the blinking LED program once more. I have here different setups for different CPU frequencies, and as usual I have a timer that I set and configure to issue interrupts in particular time intervals. And whenever there's a match, this ISR is going to execute and it toggles the LED. The new thing is this line here. So I have an assembly instruction here that is a break. This is basically a software break, and it's equivalent to the breakpoint that we had in the avr-gdb when I demonstrated the simulators. And with that, let me upload the program. The wire is disconnected. It's disconnected, so the Arduino Uno is a programmer, is an ISP programmer at the moment. And as you know, I can use avr-dude to upload this program. avr-dude, it's an M32P, AVR ISP. This is the baud rate, 19,200. This is the port, should be ACM0, and my configuration file. Hardware, tools, avr, etc, and avr-dude.conf. Let us see if it works and if the DebugWireDebuggerProgrammer is really an ISP programmer. Oh, I forgot something. Yeah, it's not AC, then it's just C, and then it should work. Okay, we have a response. The fuses are currently set to E2, so it's an 8 MHz ATmega 328p. And I forgot to give what we want to do. We want to flash the blinking LED, the hex, and it's Intel hex. Let us see if we can upload it. Yeah, that looks about right, and the LED is still blinking. Okay. So far, there's nothing special with this. We have the same functionality with the Arduino ISP. But let me activate the debugger now. So I take this wire and connect it to ground. Immediately, my target becomes unpowered. And let's see what the UART interface now tells me. So I open QtCom. The settings are 15,200, 8 data bits, read and write, no parity, and ACM0. Let's go. Breaks here, that's probably something remaining. Okay, so I have a menu here. I can identify the device and print the fuses. This uses the normal ISP interface. The low is E2, the high is DE, extend is FF, clock diff 8 is disabled, and the DebugWIRE fuse is also disabled. Now, by writing a plus, I can enable the DebugWIRE. By writing a minus, I can disable the DebugWIRE fuse. And I can even activate and deactivate the clock division by 8. Sometimes some errors happening on the data transfer between the target and the debugger, and that's why the clock divider can be activated for fast ATmegas like 16 MHz and so on. I have pretty good experience with dividing the clock by 8. In the end, you can try. Okay, let me enable the clock division. So I send an 8. And it says here now that the fuse is enabled. You can check it by writing F again. And you see that the low changed from E2 to 62. And if you check the online fuse calculator, then we'll see that if I activate this and divide the clock by 8, then this goes up and the value of the low fuse is 62. And that is exactly what I have here. If I disengage the debugger now, we go back to the programming mode, and the LED should blink slowly now. Give it a try and reset. And as you can see, the fuse is being activated, dividing the clock by 8. The green LED blinks a lot slower now. Okay, so the ISP communication works. We can reactivate the debugger. And let's see what else can we do. Okay, let's enable the DebugWIRE fuse. For that I write plus. And it says here that the fuse has been enabled. Now if I want to read the fuse bits, it says here that the clock division is still enabled and the DebugWIRE fuse has been enabled as well. And the high fuse carries a value of 9E now. That means the DebugWIRE is enabled, my SPI is still enabled, and whenever there is a reset, it goes back to the bootloader. Try to not disable this fuse to still have access to the ISP interface. Alright, what can I do now? There's one option that we haven't tried, and that is the B. So I can engage the debugger. Sometimes it doesn't work, so you can repeatedly do it, and the DebugWIRE interface is now enabled. In theory, I could remove the yellow wires now, since only the DebugWIRE is used for the communication by now. So what can I do here? Help is accepted. It throws out a lot of text. I can read the registers, for instance, and that to all of them. I can print a particular value of a register. I can set the value. I can print I/O space, that is including the extended I/O. I can even set I/O or set a bit. I can read the SRAM and the flash from particular addresses, and I can run the program and step through it and execute the reset. To exit the debugger, we can use exit, and then it allows us to remove the debugWIRE fuse again and to disable the debugWIRE functionality and return back to the normal ISP communication. Let's see what my PC is. PC is currently at 0, and at 0 address this instruction is found. Now let's check what's written there. Again, avr object dump -d -s, and then the executable. And you see here that this is my jump to CTOS end. So I'm going to execute these instructions now when I step through my program. Right, so we have here the address 68 and EOR 1,1. Then this is my ISR, here's my main program, and there's a breakpoint. That means I can run it and it will hit the breakpoint and stop there again. And now we are at address A4, it's this one. At this address there is this break. When I step to it, it sets the DDRB, so we can read out the DDRB. Unfortunately, it's not as convenient, so I cannot write something like print DDRB, but I need the address. And the address is mentioned in the reference manual, and it is one of the last entries. This one is the register summary, and this is the address, FF for instance. We see here there are some unused fields. Here's my timer 1 with the addresses of these registers, and I'm changing DDRB now. DDRB, the address is 24 and port B is 25. So I have to type in IO because that prints the value of the IO space at the location of XX. So IO 24. See, it says here it's 00, and I step one more through the program and do the same again. It says here it's 01. I'm making the first LED of port B blink, of port B0. Yeah, and that's pretty much about it. One note, the list, that is actually a bug. It's not list. The command is just L and then followed by the address. And then it prints our interrupt vector table. Then we can run the program. And as you can see, the LED is blinking as if there is no debugger at all at the desired frequency of maybe 1 second now. To stop the program at the place wherever it is at the moment, we can use break. And as you can see, the program counter is currently at the address CC, and that is my while loop. This one. And then I can continue to debug it. Okay. Now I want to unprogram the debugWIRE fuse again. So I type in exit. That means the debug wire is temporarily disabled. I can use F again and the normal menu options, and then I write minus and disable the fuse. The fuse has been disabled. And I can also disable the clock division. And that is a very short demo of the DebugWire Debugger Programmer. And I would like to thank Wayne for this opportunity and to provide this Arduino sketch. Before concluding this chapter, just one recommendation regarding the breakpoints. The program can have any number of breakpoints inserted, and they are ignored if the on-chip debug system is deactivated. However, if breakpoints are set during the debugging session, then those are so-called hardware breakpoints, and 3 of them can be set in total. In that case, a break is inserted into the program, which means that the flash page which contains the instruction at the desired breakpoint address is reprogrammed. The instruction at this address is removed and stored temporarily. The developer has to keep in mind that setting the breakpoints during debugging deteriorates the lifespan of the flash, and their recommendation is that MCUs which have been used for debugging should not be shipped to customers. Okay, what did we do in this chapter? In this chapter, we scratched a little bit on the surface of debugging for the ATmega. It is a complex topic with plenty of flavors and habits. Some developers prefer GDB, some stepping through the program using DebugWire. We also talked about simulators and hardware debuggers. Each fall into different categories with their own advantages and disadvantages. I'm hoping this chapter could give you a brief overview and help you to select the best debugging method for your project. And what is next? In the next chapter, we will talk about one of the last steps in the development process. Once the implementation is complete and tests passed successfully, your product is ready to be shipped out to the customers. A lot of efforts were put into the development, and you might want to protect the implementations against spurious analysis tools and disassembly. The ATmega has a fuse to lock the flash so that its content cannot be downloaded any longer. How to set that fuse and what needs to be considered will be the topic of the next chapter. Before heading over to the next chapter though, have a look at the exercises in which you need to get yourself familiar with the debug wire that we went through during the practical session. After that, I'll see you in the next chapter. Thanks for watching.